Hello guys, welcome to this new video. So now we are going to look through question 7 in the May 25 specimen paper 2. So here we have a star that has this black body spectrum as shown, and we firstly need to show that the surface temperature of this star is about 9000 Kelvin. So if we look in our data booklet, we'll see this relationship that the temperature of a star is just 2.9 times 10 to the minus 3 divided by the maximum wavelength emitted. So like this. So from this graph we can read off this maximum wavelength. It's approximately over here. So if we read this wavelength value off, it should be around 0.31. So all we need to do is plug this here and divide. Being careful with the units here, these are not in meters, they are in 10 to the minus 6 meters. And then if we divide this, we get 9355 Kelvin, which is approximately 9000 Kelvin. So it's important to remember this formula. It's a very simple relationship between temperature and wavelength. So the larger the wavelength, the smaller the temperature. It's a very nice inverse relationship. And then in part B, we are told the apparent brightness of this star and the distance away it is from Earth. We need to estimate the radius of this star. And well, we again just simply need to use the formulas provided in our data booklet. So we have this L is equal to 4 pi BD squared. And we also have this same formula for a given planet with the Stefan-Boltzmann times the surface times the temperature to the fourth. And well, we know this temperature, we don't know the surface area as we don't know the radius of our planet, of our star I mean. We know our distance as that's the distance away from Earth, and we also know B, the apparent brightness. So we just need to combine these equations in some way that will allow us to calculate the radius. So we know A is 4 pi r squared. That's just the surface area of a sphere, like this. And if we rearrange this for r, we'll find that this is L divided by 4 pi sigma t to the 4. And this is all under the square root. And well, we can calculate this L value from this formula, and we can just plug this in here. And so we'll find this equation of square root 4 pi BD squared divided by 4 pi sigma t to the fourth. The 4 pi's cancel out, and we just need to plug in all of our values. So apparent brightness was 2.2 times 10 to the minus 9 times the distance squared, so 6.2 times 10 to the 17. So it's important here that we work in meters if we want the radius also in meters. And then we divide by the Stefan-Boltzmann constant, so 5.6 times 67 times 10 to the minus 8 times the temperature. Here we are allowed to use the more precise temperature we calculated here. We should only use this 9000 if we weren't able to calculate this more precise value, but it wasn't too difficult. And then this will give us a radius of 1.3, and the distance should be squared. I forgot a 2 from here. And this is to the fourth. So the distance is 1.39 times 10 to the 9 meters. In the last part of this question, we are given the radius of the sun, and we need to sketch on this HR diagram the position of the star. Well, we know the temperature of our star is approximately 9000 Kelvin. So if we look, that should be somewhere along this line. As on this horizontal axis we have temperature, and then we have these lines of constant radius, and so we need to determine the radius of our star. I mean, we already know the radius, it's 1.3 times 10 to the 9 meters, and well, we can convert both to similar units, so we can say that this is 0.7 times 10 to the 9 meters. So what we see is that the radius of our star is approximately double the radius of the sun. So we can say that r is equal to approximately 2 times R0. And well, so now we can kind of already see this ratio. So these lines are corresponding to certain multiples of the radius of the sun. And well, it's times 2, so it's somewhere a little bit above this this 1R line, as this is corresponding for 1 times the radius, this is 10 times the radius, so somewhere in between. So we can draw it somewhere over here. And so this is how you solve question 7 in this paper. I hope I was able to help, and see you in the next video.